Hi, and welcome back to the talk. I'm Shruti, and today we're talking about cross-lingual entity linking for low-resource languages. In the previous part of the talk, we discussed pivot-based entity linking, a method that uses no resources in the source language for training, but rather relies on zero-shot transfer and pivoting for candidate retrieval in low-resource settings. In this part of the talk, I will present an extensive analysis of the errors made by the pivoting model and how, while retaining the same core ideas, model and data modifications can result in much better candidate retrieval performance. Although pivot-based entity linking performs better on low-resource languages than existing translation-based methods, significant room for improvement remains. To identify potential areas of improvement, we do a systematic analysis of the errors made by the model, inspecting 100 errors from each of 4 low-resource languages in the dataset, and manually classifying these errors into several types. We use mentions in the Marathi language as examples of the types of inputs that led to entity linking errors. The first type is the direct mention class, where the mention and the target knowledge base entry are essentially transliterated and have a direct word-by-word mapping. As seen here in the Romanized Marathi entity, it contains the same words as the corresponding English knowledge base entry. The second mention class is the alias class, where the mention is an alternate name of the target English entry. Such mentions cannot be resolved by the entity linking model in its current form because it is only trained on one name per target entry and doesn't consider any aliases. The next error we identify is the translation error. Although named entities are typically transliterated across languages, common words like university are often translated, as you can see in the example here. The pivot-based model is unable to resolve most of these because it is primarily trained on transliterated data. Finally, we also find that the model cannot successfully find the entity link if an extra word is present in either the mention or the knowledge base entry. For example, honorifics like sir or titles like president may be present in one side, but not the other for the same entity. We create 3 classes for the position of the correct knowledge base entry in the candidate list. The first shows whether the correct entity link is the top scoring entry, which means the correct entity is ranked the highest and the prediction is successful without a disambiguation model. The second shows whether the correct link is not ranked the highest, but is in the top 30 list and can be selected with a downstream disambiguation system when it is given the candidates as input. The third indicates that the correct link is outside the top 30 list altogether and cannot be recovered by the downstream disambiguation model. The figure shows the distribution of the predictions for each mention type with the pivot-based entity linking model. We see that even for simple word-by-word direct cases, the model often fails to include the correct link in the top 30 candidate list. We also see that the model almost always fails on alias and translation mention types. Having such a large number of mentions without the correct link in the candidate list strongly limits the end-to-end entity linking performance. That's why, motivated by this analysis, we present 3 modifications to the model, as well as to the data used for training, in order to improve candidate retrieval, while still not requiring any resources in the source language. First, we note that there is a difference between the types of mentions in the test data as compared to those the pivoting-based model is trained with. The model is trained with entity-entity pairs from Wikipedia language links, and these are word-by-word mapped pairs. However, the model can be queried with other types of mentions. For example, a document can refer to a person entity by their last name. Because the entity linking model only learns word-by-word matches, it cannot resolve more complex matching patterns, such as these partially matching names, which are really important in the candidate retrieval process. As a solution, we propose to add mention entity pairs to the training data, which are collected from articles and pages in the Wikipedia of the high resource language. Consider this example where the trained language is Hindi and the test language is Marathi. The pivot-based model is trained to compute similarity only on the full names of the entities, as seen here, because its training data is derived from the article titles in Hindi Wikipedia. When we add mention entity pairs from the Hindi Wikipedia to the data, the model is also trained with different realizations of the same entity, such as partial matches like Kobe corresponding to Kobe Bryant. These mentions are derived from the text contained in the Wikipedia articles, where links to a specific article from other pages are often different surface forms of the same entity. Additionally, it is very hard for a string matching model to know that two very distinct strings actually refer to a single entity without additional information. This is because entity aliases often have very little word overlap. To account for such cases, we use Wikidata, a large-scale encyclopedia that already contains a large number of aliases for entities in English. For example, consider the Wikidata entry for the entity Kobe Smulders, which lists other known names of the person. These are also connected to the main Wikipedia entry for Kobe Smulders, which is what we would actually want to use for entity linking. At test time, apart from the similarity score with the original knowledge base entry, we also calculate the score between the input mention and all the Wikidata aliases for that knowledge base entry using the trained model. The maximum similarity score among all the aliases and through the pivoting method serves as the final score for that knowledge base entry. Recall that the pivoting method makes errors on simple direct cases where the mention and the entity are transliterations of each other and have a word-by-word mapping. Because of the large number of such errors, we suspect that the BILSTM encodings from the model do not capture the information from the string optimally for entity linking. We replace both the BILSTMs in the model with a more explicit string encoder, which is a character-based n-gram model called charagram. The charagram model treats a string as a bag of character n-grams. It then finds the embedding for each n-gram through a lookup table, and the final string embedding is the sum of all the n-gram embeddings followed by a non-linear activation function. Overall, the charagram model provides a more direct and explicit way to encode strings as compared to the BILSTM, which will be demonstrated in the empirical results that we'll see next. Using the core ideas of the pivoting method that we introduced in the previous part of the talk, in this part, we discuss modifications based on an in-depth analysis of the entity linking results from that method. The first of these modifications is adding mention entity pairs to the training data in order to eliminate the discrepancy between the train and test mention types. We also add Wikidata aliases to make it easier for the model to link less common names of the same entity. And finally, we replace the LSTMs in the model with charagram, which is an encoder that explicitly models character n-grams in the strings. The model is trained similarly to the original pivoting method. It is trained only on high resource language data, and the zero-shot transfer and pivoting techniques that we discussed previously are still applied here. To evaluate whether the proposed modifications to the model are effective, we compared the top 30 candidate recall between the original pivot-based entity linking method, or PBEL, and the modified method, which we call PBEL+. The top 30 recall metric refers to whether the correct candidate link for the input mention is present in a list containing the top 30 highest scoring entities from the model. The figure shows the top 30 recall for both the PBEL and the PBEL plus methods, and we see that the modifications improve the recall for 6 out of the 7 low resource languages in our experimental setup. On average, we see an almost 20-point increase in recall. We also look at the errors made by the new model based on the categories of mentions that we classified earlier. Compared to the original pivoting model, a large number of errors are eliminated and more mentions have the correct entity as the highest scoring knowledge base entry in the candidate list. We also see a significant improvement in both the direct and alias mention types, with more correct entities in the top 30 candidate lists, which provides the downstream disambiguation system with a larger headroom for improvement. A number of translation mention errors are resolved as well. To conclude, in this part, we presented a systematic error analysis over the pivot-based entity linking method and discussed modifications to highlight the diverse realizations of a mention, as well as of the unique identification of an entity. We also replaced the LSTM encoders with character n-gram-based encoders that improve string representations in the model. The adapted model results in a significant improvement in recall over 7 low resource languages. With this improved candidate recall method, in the last part of the talk, I will discuss how these candidate lists can be incorporated into neural named entity recognition models to improve performance in low resource settings.